I now call to order the Society's 2,436th meeting in the 149th year since its founding on March 13th, 1871. Good evening, everyone, and welcome to PSW Science's Spring 2021 meeting and lecture series. Because of COVID-19, the Society is bringing this meeting to you via Zoom from locations all around the globe, rather than our usual home, the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. This evening's lecture will be about the giant Magellan telescope, now being built in the rarefied atmosphere of the Andes in Chile. When completed, it will have 10 times the resolving power of the Hubble Space Telescope. Our speaker is James Fanson, Project Director for the GMT. I'm Larry Milstein, President and Program Director of PSW Science, one of the oldest scientific societies of Washington, D.C., founded in 1871 as the Philosophical Society of Washington, to provide a forum to exchange scientific ideas, further scientific understanding, and encourage scientific inquiry, a mission it continues to this day. This lecture is being recorded and will be posted to the PSW Science YouTube channel, where it will join over 150 other recordings of PSW Science lectures. We invite you to explore these presentations and to become a member through the PSW Science website, www.pswscience.org. The Society is grateful for the sponsorships of the 2020-2021 lecture series by the Policy Studies Organization in cooperation with the American Public University and by a donor who was asked to remain anonymous. PSW thanks all of its sponsors. Before we turn to the lecture, in keeping with the Society's traditions, we will welcome new members and read the minutes of the previous meeting and the summary of the previous meeting's lecture. I'm very pleased to announce that the following members have been elected to the Society. Giovanni Aurelio, an independent consulting engineer, interested in all things having to do with engineering, who learned of PSW Science from PSW member Miles Taylor. Giuseppe Aurelio, an aeronautical engineer, interested in mechanical and aeronautical engineering, who learned of PSW, again, from PSW member Miles Taylor. Patricia Mott, a lawyer, retired from the EPA, interested in astronomy, who learned of PSW Science from an article in the Washington Post. And Jim Fanson, our speaker tonight, who learned of PSW through our invitation to him to give tonight's lecture. Some of his interests will be clear from tonight's presentation. We welcome them all to membership. Membership is a most important pillar of the Society. I encourage everyone with an interest in science to become a member. It's easy to do using the PSW Science website, www.pswscience.org. PSW is a 501c3 charitable education and professional organization. Dues payments and other donations to PSW are tax deductible. Recording Secretary James Heelan will now read the minutes of the 2,435th meeting and the lecture by Nikki Fox on the Parker Solar Probe. James?
Thanks, Larry. On February 19th, 2021, by Zoom video conference broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2,435th meeting of the Society to order at 8:02 p.m. Eastern Standard Time. He announced the order of business. welcomed new members, and read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, Nicola Fox, Heliophysics Division Director and the Science Mission Directorate at NASA. Her lecture was titled HOT, the Parker Solar Probe, Heliophysics Near the Edge of the Sun. In 2020, NASA's Heliophysics Division grew to a total of 20 operating missions with a total of 27 spacecraft, 11 missions in formulation, and 9 further missions under study. In addition to providing Earth with an early warning system for solar weather, the Heliophysics Division spacecraft are seeking answers to long-standing mysteries of solar physics. Why is the corona hotter than the solar surface? Where does the solar wind originate and how is it accelerated? How are solar energetic particles accelerated and transported? In 1958, Eugene Parker published a paper predicting the solar wind would break away from the pull of the sun and bathe the planets in a protective field. Parker has told Fox he reached his findings merely by solving 6 fairly simple equations. Among Parker's predictions was solar wind acceleration. 60 years after Eugene Parker's paper, on August 12, 2018, NASA launched the Parker Solar Probe atop a Delta IV with an upper stage. The probe is humanity's first visit to a star. Parker's sister mission, the ESA Solar Orbiter, launched in early 2020 and will conduct coordinated measurements. At launch, the probe had a wet mass of 685 kilograms and stood 3 meters tall. Fox said the payload needed to remain as light as possible to avoid being dragged at launch by Earth's angular momentum. She then described NASA's decision to include momentum wheels on the spacecraft. The Parker Solar Probe is in a region of plasma approximately 3 million degrees Celsius. Fox said that because the plasma itself is not very dense, NASA's greater concern for the spacecraft is heat from illumination. That illumination is reflected by a white cover in front of a 4.5-inch thick carbon composite heat shield attached to the main vehicle by only 6 carbon bolts. The front side of the heat shield reaches approximately 1400 degrees Celsius, while the main body of the spacecraft stays between 28 and 30 degrees Celsius. The spacecraft is powered by liquid-cooled solar panels designed to operate under extreme solar flux. The articulated panels flap according to the probe's proximity to the sun to generate consistent power. Fox then described the probe's launch using video and vivid animations. After launch, the spacecraft made its first orbit of Venus to slow itself down. It will make 24 orbits of Venus over the lifetime of its mission. Each orbit will send the probe closer to the sun. After the 7th, the probe will be traveling at approximately 430 miles per hour and pass 3.9 million miles from the sun's surface through the solar corona. The Parker Solar Probe carries 4 instrument suites. These instruments are used to conduct the field experiment, designed to study magnetic fields, the solar wind electrons, alphas, and protons, or SWEEP investigation, the Integrated Science Investigation of the Sun, or ISIS, to observe energetic particles, and the Wide Field Imager for Solar Probe, or WISPR, to image the solar corona and inner heliosphere. Fox then described Parker's current science results. She showed an animated compilation of the probe's imaging of the solar corona at resolutions impossible from observation at further distances. The WISPR instrument has made multiple discoveries. The imager has confirmed the existence of magnetic islands where particles can be trapped, energized, and heated. It is also on the verge of confirming the existence of a dust-free zone around the sun. The probe's observations have identified unexpected magnetic structures in the young solar wind. These switchbacks are a potential energy source for coronal heating. And the probe has discovered extended co-rotation of the solar wind. Fox concluded by discussing the ongoing journeys of the Voyager 1 and Voyager 2 spacecraft through the outer solar system environment. Voyager 1 was the first to cross the heliopause boundary, but did not have a functioning solar wind instrument at the time. In 2018, scientists were able to confirm Voyager 2 exited the heliosphere because its energetic particle detectors identified dramatic changes in the ratio of heliospheric particles to galactic cosmic rays. The speaker then answered questions from the online viewing audience. One member asked about how the Parker Solar Probe communicated with Earth. Fox said the probe stores approximately 250 gigabits of data per orbit onto a solid-state data recorder. NASA uses X-band to send commands to the probe and downlinks data on a Ka band when the probe nears Earth. Another member asked about the latitude at which the probe observes the sun. Fox said the probe stays in the ecliptic and does not observe any other latitudes. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 10:03 p.m., President Milstein adjourned the meeting. The temperature in Washington, D.C., 3 degrees Celsius. Weather, partly cloudy. Number of concurrent viewers on the Zoom and YouTube live stream, 110. And views on the PSW Science YouTube and Vimeo channels, 328. Respectfully submitted, James Hewlin, Recording Secretary.
Thank you, James. The minutes will be posted in due course to the website. Please send any corrections or comments on the minutes to Corresponding Secretary Robin Taylor at corresponding@pswscience.org. A video of the lecture is available to everyone without charge on the PSW Science YouTube channel, the PSW Science Vimeo channel, and it can be accessed directly from the PSW Science website, www.pswscience.org. We now turn to tonight's lecture. It's my pleasure to introduce tonight's speaker, James Fanson. Jim is project manager for the Giant Magellan Telescope. Prior to taking on the role of project manager with GMTO, he was with JPL for 30 years, serving as project manager for the Galaxy Evolution Explorer, the Keck Interferometer, and the Kepler mission, leading the preliminary design team for the Spitzer Space Telescope, and serving on the team that rescued the optical performance of the Hubble Space Telescope. Among other honors and awards, Jim received 2 NASA Outstanding Leadership Medals, a NASA Engineering Achievement Medal, NASA's Allen Award for Excellence, the National Space Club Goddard Trophy, the Smithsonian Air and Space Museum Trophy, and he was program manager on the Kepler team that received the Aviation Week Laureate Award. Jim earned his PhD in Applied Mechanics at Caltech. All questions will be fielded in the Q&A session after the lecture. Jim, the screen is yours.
Thank you, Larry, and thank you all for attending my talk. I'm going to share my screen. And get the proper cursor. Can you see my slides?
You're good.
Very good. All right. I'm going to talk to you about the building of the Giant Magellan Telescope. I'm going to start by reviewing a bit of the history of the telescope, explaining why it is we continually want to build a bigger telescope. Talk to you a bit about some of the engineering challenges we face and some of the science that we anticipate doing. I'm going to start with the human eye, which is actually a remarkable optical system, and it functions a bit like a simple telescope. The human eye has a pupil that allows light in and a lens which focuses the light, and it has what we would call an aperture of about 0.2 square centimeters. That's the area of the pupil when it's dilated by a bit. And with the human eye on a dark adapted night, you can see about 6,000 stars in the sky, and that's about it. anything that is very far away is generally too faint. The faintest distant object, or I should say the most distant object you can see with the naked eye, is the Andromeda Galaxy. But beyond that, you need assistance. The human eye needs assistance. So principally, the telescope has been invented to allow us to see things that are far away, look at them more up close, and to allow us to see things that are too faint to be seen with the unaided eye. The first person that we know of to turn a telescope to the heavens was Galileo back in 1609. And he took meticulous notes, and we know that with his telescope, which had only a 1-inch aperture with a lens in the front of a tube, he was able to discover that the moon had craters and mountains, that the sun had sunspots, that the sun seemed to rotate, and that the planet Venus went through various phases, which supported the theory that the planets, including the Earth, orbited the sun rather than the other way around. And it was revolutionary. It transformed our understanding of the solar system. Galileo also discovered that there were 4 moons that orbited the planet Jupiter, and those moons are now named after him as Galilean satellites. Then telescope technology progressed, and the largest telescope of the same type that Galileo had built, so-called refracting telescope with a lens in the front, was the Yerkes 40-inch telescope with a 1-meter lens, which was commissioned and made its first observations in 1897. It was financed by Charles Yerkes from Chicago. You can see his face in the edifice of the beautiful building there at Lake Geneva. But with 1-meter lenses, refracting telescopes reach their limit. And this is a recurring theme in telescopes, is that you want to build the largest telescope that your technology will support and that your pocketbook can afford. And typically the most important element in a telescope is the light gathering lens, or as we'll see now, mirrors. Lenses above 1 meter in size are very difficult to manufacture. And so telescope makers turn to reflective telescopes using mirrors instead of lenses after this point. One of the most famous telescopes is the Hooker telescope, the 100-inch telescope on Mount Wilson that was built by George Ellery Hale. And this is the telescope that Edwin Hubble used to discover that there are galaxies outside of the Milky Way, and to discover the expansion of the universe. Again, transforming our understanding of the size, scale, and our place in the universe. On the right-hand side is perhaps the most famous photograph ever taken in astronomy. This is the so-called VAR plate, which resides in a plate vault at the Carnegie Observatories in Pasadena. This is an image of the Andromeda Galaxy, and Hubble was looking for variable stars and discovered a variable star of a particular type that allowed him then to infer the distance to the Andromeda Galaxy, and that's how our understanding of the scale of the universe was transformed. Then George Ellery Hale went on to build a 200-inch telescope, so-called Hale telescope, named after him at Palomar Mountain. The mirror for this telescope was cast in 1934, and it was a heroic struggle to figure out how to manufacture a mirror that was 5 meters in diameter. You can see it on the right. You're looking at the back surface. The light weighting pockets are visible. The reflective surface is on the other side. And if you're interested in the story of this telescope, there's a marvelous book written by Ronald Florence called The Perfect Machine, which will take you through all the trials, tribulations, inventions, and geniuses involved in the building of this telescope. It was interrupted by the Second World War, but saw first light in 1949. And building a larger mirror than 5 meters was so formidable that no larger working telescope was built until the Keck telescope in the 1990s. So for 40 years or more, the Palomar 5 meter was the world's largest scientific telescope. But then by the 1990s, technology had progressed in terms of computer control equipment and photoelectric sensors that made it possible to conceive of a telescope that could be built with a segmented primary mirror. So Jerry Nelson at the Lawrence Berkeley Laboratory had a bold concept that one could mosaic a series of hexagonal mirror segments, and you can see a mirror segment on the right-hand side, about 1.8 meter from flat to flat. Take 36 of these segments and then using edge sensors and computer control, align these segments as though they formed a single mirror surface. And and to do that is called phasing of the mirror segments, and they have to be phased within a small fraction of the wavelength of light that you're observing. So that was a formidable undertaking, and many people felt that this was an impossible task, but indeed, the Keck telescope was a tremendous success. It broke the 5 meter aperture barrier and achieved a 10 meter aperture. We're now talking about a light gathering power of a telescope that's 4 million times the light that can enter the human eye. Around the same time, people were working on technologies to build larger monolithic mirrors. And one of those techniques, the spin cast mirror technology, was developed by Roger Angel at the University of Arizona. And you can see on the left image an 8.4 meter spin cast mirror side by side now to scale with the Hale 5 meter telescope mirror. And you can see the light weighting pockets again on the back surface. So this technology enabled a series of telescopes with very large monolithic mirrors. And the advantage of having monolithic mirrors is that every time you introduce an edge to incoming light from a heavenly object, there's a scattering of light that occurs, a diffraction effect that occurs with light, which reduces the contrast of the image and creates other difficulties. And so the quality of imaging of a telescope is enhanced if you can minimize the edges. And that's one advantage of having a large monolithic mirror. So it's interesting to plot as a function of time the largest telescope in the world. And if you plot it on a log scale, you can fit with a pretty good correlation, a straight line in that plot. And you discover that over time, since the time of Galileo, that the world's largest telescope basically doubles in size about every 30 years. And this is because of the advance of technology. You also discover that it becomes less expensive per unit of telescope aperture, again, because of advanced manufacturing techniques and technology. So the current generation of 8 and 10 meter telescopes today was developed in the 90s and the zeros. And so it's time, actually, and I'm going to figure out why my cursor has disappeared. Give me a moment here. Get my cursor back. The current generation of telescopes was built about 30 years ago. So it's time now for the next doubling. And indeed, there are now 3 so-called extremely large telescopes that are in development across the world: the Giant Magellan Telescope, the 30 meter telescope, and the European Extremely Large Telescope, or European ELT. And these are scheduled to come online in the next 10 or 15 years. And so the Giant Magellan Telescope is going to take its place as a 25 meter telescope. And what we're doing is taking advantage of these 2 breakthroughs that occurred in the 20th century. The segmented primary mirror and computer control, as well as the very large monolithic mirror technology. So what we are going to do is form a primary mirror out of 7 individual mirror segments, each of which is 8.4 meters in diameter. And that will give us a telescope with 19 million times the light gathering power of the human eye. Truly staggering capability. Now, it's interesting to look at the benefit of a large telescope from the point of view of the physics of light. So one of the important aspects when you're looking at objects that are deep in the universe, far away and therefore very faint, is you want to gather as much light as possible, because when you're studying celestial objects, it's not just the imaging you want to do, you want to take spectra of these objects. And the spectra allows you to determine the composition of what you're looking at, the physical processes that are going on in that object. You can say something about the chemistry that's taking place. And to take a spectra means you have to disperse the light, spread the light out, if you will, spectrally, to take its fingerprint, so to speak. And you need a lot of light in order to be able to have a reasonable signal to noise ratio. So if you want to see fainter objects, and you want to gather more light, and you need a large telescope. Of course, the amount of light that a telescope gathers goes with the square of the aperture. But due to the physical nature of light, the resolution or the amount of detail that you can observe in an object increases linearly with the aperture of the telescope. So a telescope that has twice the diameter will be able to image with twice the imaging resolution, provided you can correct for the distortion effect of the Earth's atmosphere. And I'm going to spend some bit of time talking about that. So the way we correct for atmospheric distortion is with a technology we call adaptive optics, also a 20th century technology. So when you see the term AO, you're going to know what that's referring to. So I'm going to show you some comparisons here of a collection of stars in the near infrared part of the spectrum. And this is the resolution that a telescope would have if you were observing through the Earth's atmosphere from a reasonably good observing site on the Earth. And it would not matter how large your telescope is, because the inherent resolution is limited by the native atmosphere. And I'll explain a little bit more later why that is. But if you're able then to correct for the Earth's atmosphere and achieve the diffraction limit, or if you could go into orbit above the Earth's atmosphere into space, this is a comparison of the kind of imaging resolution you can achieve. So this is a Hubble Space Telescope, which has a 2.4 meter aperture, again in the near infrared. This is the resolution of that same scene that we would expect to see from the James Webb Space Telescope, which NASA is scheduled to launch later this year, which is a 6.5 meter aperture. And then with a 25 meter aperture, the aperture of the giant Magellan telescope, this is the kind of resolution you could achieve. So if you want to look in detail at objects, or you want to look very close to an object, for example, looking for an exoplanet orbiting another star, you have to look very close to the star to find the planet. Or if you want to understand what's going on close to the event horizon of a black hole, you need to look close to the black hole. If you want that kind of imaging resolution, you need a larger telescope. So these two features of gathering more light and having inherently higher resolution are what drive us basically to want to build ever larger telescopes. Now this image taken by the Hubble Space Telescope is called the Ultra Deep Field. This is an image that was taken of about the most empty part of the sky that NASA could identify. And you have to remember that the field of view of the Hubble telescope is quite small. It's about a grain of sand held at arm's length. That's how much of the sky it observes at any given time. And this is a small fraction of that field. And what you're seeing here, essentially every object in this image is a galaxy deep in the universe. So these are not stars in our galaxy. These are separate galaxies, and they're quite distant. And the more distant a galaxy is, the more or further back in time you're observing, because of the finite speed of light. It takes light time to travel through space from one point to another. And as we look deeper in the universe, we're looking back in time. We're seeing the universe as it was in the distant past. We know from astronomical observations that the universe began in a big bang that occurred about 13.8 billion years ago. And when you look at this image, there are certain objects that are so far away, they're so far back in time that the light has been stretched and shifted into the red. And these objects are very distant indeed. When you blow up what the Hubble images of these objects look like, you're looking at some of the earliest galaxies after the Big Bang. These are galaxies that are less than 300 million years old after the Big Bang. And we're very interested in understanding how the first stars and galaxies formed. And when you look at galaxies from the early epoch of cosmic history, you see they look quite different than galaxies do today, like our Milky Way galaxy. So we very much want to be able to study these objects in greater detail and to take spectra of these objects to understand the physical processes that are taking place. If we look a bit later in the age of the galaxy, this is a redshift of 2. This corresponds to what astronomers call cosmic noon. This is a period of time in the evolution of the universe where star formation seems to have reached a maximum. And understanding how galaxies assembled themselves out of stars that are forming is key to understanding galaxy evolution and how galaxies came to be the way they are and how stars and systems formed. So if you were to take a current 8-meter telescope, this is what you would see from the Gemini telescope on the right, against a synthetic image of what the galaxy really looks like on the left. Even with adaptive optics to correct for the atmosphere, this object is so far away and so faint that the resolution you can achieve is quite limited. However, moving to a 25-meter telescope, like the Giant Magellan telescope, this is what we would expect to be able to image. So we would now be able to take spectra of individual regions of the galaxy and begin to understand better how galaxies formed and evolved over cosmic time. So a consortium of institutions have joined forces to build the Giant Magellan telescope. They're listed here. I'm not going to name them all. And we've chosen to locate our telescope at the Las Campanas Observatory site in the southern end of the Atacama Desert in the Chilean Andes. This is land that is owned by the Carnegie Institution for Science, which is one of our founder institutions, and where they have their twin 6.5-meter Magellan telescopes located. So we're going to locate at that same site, and we will be the Giant Magellan telescope. Where to locate a telescope is a really important issue. There are essentially 4 features you're looking for locating a site for a giant telescope. One is you want a site, obviously, that's dark, particularly if you're an optical infrared telescope. You want something free of light pollution. You want something that is a site that is cloud-free, so you have no obstructions to observing the heavens. And you want dry air because, in particular, the moisture in air absorbs light. And there are regions of the spectrum that you cannot observe through the Earth's atmosphere. And the more moisture you have, the more absorption that occurs. This is what tends to drive telescopes to mountaintops. You have less atmosphere above you when you're at high altitude. And then importantly, you want steady air. And the reason for that is that the Earth's atmosphere is really composed of cells of air that are, each cell is at a different temperature. And the refractive index of air changes with its temperature. And as the light from a celestial object arrives at the Earth, it's traveled all the way across the universe to reach us. And you can think of the wave as the wave nature of light. You can think of these expanding spherical waves of light coming across the universe. By the time they reach us, they're basically flat. And so you get these beautiful plane waves of light striking the atmosphere, and then they go through this turbulent, unsteady air, and the wavefront gets all distorted. And this is what causes stars to twinkle when you look at them with your naked eye. And this is what means that any telescope is going to have a limited resolution, limited by the atmosphere, by this effect. But you can minimize this effect by selecting a site on the ground that has very smooth and steady air. By the way, I'm going to come back to this adaptive optics topic, which is a technology we use to combat this effect. And AO works best at sites that already start out with as stable and smooth an air as possible. So this tends to drive you to locations on the Earth that are either mid-ocean volcanic island peaks or continental coastal mountains where you have smooth air flowing from the ocean over the continent. And this is why you tend to find the world's largest telescopes on mountain peaks in Hawaii, on Mauna Kea or Haleakala, or in the Canary Islands, or in the Southern Hemisphere in the Chilean Andes, which is where we are locating. Now, of course, as I said before, the ultimate best place to observe the heavens is from space, where you get above the atmosphere. But getting to space is a difficult task and comes with its own challenges. So this is an artist rendering of what the completed Giant Magellan Telescope Observatory will look like. It's a very dry location. There's more than 300 nights of clear air with exceptionally steady airflow. I'll point out a couple of features here. This is the building that houses and protects the telescope that we call the enclosure. This building to the left of the enclosure is where we process and coat the primary mirror segments, and I'll say more about that. And then all the noisy machinery, the rotating pumps and so on that supply fluids and coolants and air conditioning and so on are located away from the telescope. And then we have our water storage and distribution system. So this is what the completed observatory will look like. I'll show you later on a drone image of what the site looks like at the moment. Now, it's a little hard to tell the scale from this image out in the Atacama Desert. So if we relocate the observatory into the Rose Bowl in Pasadena, this is what it would look like. So it's enclosure's about 60 meters in diameter, about 65 meters high, and is quite an undertaking in and of itself. Has many specialized functions that have to work in concert with the telescope. All right. Now, there are a number of novel features of the Giant Magellan Telescope. Most modern telescopes, whether they're on the ground or in space, are of a reflecting telescope design with a primary mirror and a secondary mirror. In our case, this primary mirror and the secondary mirror are segmented. So there's 7 segments in each of the primary and secondary mirror. And they operate in pairs. So as light comes into the telescope from a heavenly object, it will first strike a primary mirror and then be reflected and strike a corresponding secondary mirror, and then proceed down through a hole in the center segment to reach the scientific instruments that make the scientific measurements. Our telescope follows what's called a Gregorian optical design. This is a design that was invented by the Scottish mathematician James Gregory, who was a contemporary of Isaac Newton. However, most telescopes today you'll find are made to the Ritchie-Chrétien configuration. The Hubble telescope, the Keck telescope, those are Ritchie-Chrétien designs. And one of the interesting aspects of the Gregorian, and one of the reasons we like it, is that in the Gregorian design, both the primary mirror and the secondary mirror are concave. In the Ritchie-Chrétien design, the secondary mirror is convex, which is more difficult to manufacture. Another advantage is that the light comes to a focus before it reaches the secondary mirror and reflects down to the scientific instruments. And this allows us to do things like place point sources of light to calibrate our adaptive optic system and do other calibrations more conveniently. And finally, the Gregorian design gives us a very compact plate scale, which means that our scientific instruments are much more modest in size and complexity, easier and cheaper to manufacture, and it gives us a very large field of view that we can achieve. So some of the challenges that we face is that because our primary and secondary mirror are both segmented, we need to find a way to do an alignment of this system and to phase the telescope. And no one has ever built a doubly segmented telescope and phased it before. So we know and understand that this is a challenge. Now, looking at the arrangement of primary mirror segments, just to give you again a sense of scale, the primary mirror segments are 8.4 meters in diameter in our case. The hole in the center segment is 2.4 meters, which just turns out to be the size of the mirror in the Hubble Space Telescope. So you can see the challenge of putting telescopes in space. You have to put them on a rocket and get them into orbit. That's a difficult thing to do, and it tends to limit the size of the telescope you can get into space. The James Webb Space Telescope, which NASA will launch later this year, is by far the largest telescope ever to go into space at 6.5 meters. But by ground-based standards, by the standards of the extremely large telescopes, James Webb will still be a small telescope. So the amount of light it can gather will be small by comparison. And there's a human figure there for scale at the bottom. All right, I'm going to take you on a tour now of the Giant Magellan Telescope. I'm going to run a video and I'm going to narrate as we go through here. We zoom in to the enclosure with the biparting doors opening. You can see the telescope beginning to tilt downward on its elevation axis, and the mirror covers open. The mirror covers protect the reflective surface of the primary mirror segments. As we descend, you see these red colored portions of the telescope. Those are the mirror cells. And I'll show you a photograph of a prototype cell. And you can see the curved C-rings of the elevation axis. And below them is the azimuth axis. So this is an elevation azimuth mount with hydrostatic bearings. So these bearings float on a thin film of oil. Now, zooming into the center of the telescope, let me let this run a little further. This is where the scientific instruments are located. And the instruments are all attached or mounted to what we call the Gregorian instrument rotator, which is a 6 meter by 9 meter cylinder. And all the scientific instruments, our acquisition, guiding, and wavefront sensing system are attached to the cylinder, and the cylinder rotates along it about its long axis in order to derotate the image rotation that occurs as the telescope tracks an object across the sky. So this is also a unique feature of GMT, and this precision motion adds a third axis of rotation to the telescope. Now, mounted on the top of the GIR of the 6 by 9 meter cylinder are instruments that receive their light. The light comes down from the telescope above, strikes a tertiary mirror, and then is directed into one of these scientific instruments. If we continue the video and descend into the interior of the GIR, we have another set of scientific instruments we call direct Gregorian instruments. We call them direct because the light comes directly from the secondary mirror of the telescope into the scientific instrument. So there are only two reflections. And this is important because every reflection causes a loss of light. So if you lose, a percent per reflection, soon, you're starting to lose significant light. So the fewer the reflections, the better. And our design can deliver light to instruments with only two reflections. So I'm going to walk you through now how these giant mirrors are manufactured. They are cast in a spinning mold inside a spinning furnace. This is a photograph taken at the Richard F. Karras Mirror Laboratory at the University of Arizona. All of this mirror production occurs underneath the football stadium at the University of Arizona. And what you're looking at is the furnace with the lid removed, and the technicians are building up the mold. And there are 1,700 individually machined silica alumina blocks, and they each have a different configuration, a different shape, and they're separated by a 1/2 inch gap. And once the glass flows into this mold, this forms the honeycomb structure, which lightweights the mirror. These mirrors are 80% lightweighted, so they're very stiff, but they're comparatively lightweight. Once the mold is in place, then borosilicate glass that's manufactured in small batches in Japan are placed by hand in the mold. There's about 20 tons of glass that's placed in the mold for each of these castings. You can see the technicians there carefully placing the glass. And then the furnace is heated up and spun. And when the temperature reaches the melting point of the glass flows and is propelled by the centrifugal force of the spinning into the mold, and it forms a parabolic surface on the top front surface of the mirror, which makes it much closer to the final net shape of the mirror and saves a lot of time from having to grind that glass away. It comes close to the near net shape. Now I'm going to next run you a time-lapse video of this process, and it runs a little too fast to narrate, but at least you'll have some context for what you're looking at. So this is the construction of the mold on the floor of the rotating furnace. This is the refractory material, which is held together by Inconel bands to take the stress. Then the cores are installed. These are the machined cores that form the honeycomb pattern. And next you'll see the glass laid in the mold. And then the lid is put on for the final time. It's heated up and spun. And this is a camera inside the mold. You can see the glass melt, flow together, and achieve the right expected level. This is how we know we've had a successful casting. And then the oven is opened, the form is removed, and we glue on a lifting fixture and lift the mirror out of the furnace, out of the mold. So we have now cast 5 of the 7 segments that are needed for the Giant Magellan Telescope. The 6th mirror is being cast as we speak, and the high temperature will occur early tomorrow afternoon. And if all goes well, we'll have the 6th segment cast and have only one to go to form the primary mirror. This is what it looks like when it's out of the mold. There's a careful inspection performed. You can see someone gingerly walking on the front surface. It's then lifted, and all the refractory material is cleared out, leaving all of these hollow lightweighting areas. This is the rear surface of segment 5. And then we bond onto the back surface attachment points in order to support the mirror. The mirror This is the rear surface with what we call load spreaders bonded on. There are about 165 pneumatic actuators, force actuators, that support the mirror when it's in operation. In some sense, the mirror rests on a bed of nails, but each of these nails is a force actuator that we can control very precisely the amount of force applied to the mirror. And this allows us to keep the mirror in the correct shape. So the mirror has to be to the desired shape to very high precision in order to achieve diffraction limited imaging. We then rotate the mirror over and begin polishing the front surface. This shows mirror segment 1 under the polisher, and you can see there's an active lap located here. This is a computer-controlled lap that varies the forces on the lap. Now, because these mirror segments, the 6 outer ring segments of the Giant Magellan Telescope are off-axis, so they have a bit of a potato chip shape to them, which is a complex shape to polish into a mirror. So no mirror this size had ever been polished into an off-axis shape, and so considerable time was spent proving that we could do that. And this is the segment that was proved on. And the polishing has to be precise to about 1/1,000,000th of an inch. Again, that's a fraction of the wavelength of light that you're observing in. Once the polishing is complete, we put a protective layer, a strippable layer over the reflective surface, and lift it with a collection of suction cups and a crane, and place it into a shock-mounted steel transport container to protect it for its 5,000-mile journey to Chile. We have 2 completed mirrors now. They're in storage in Tucson, awaiting their shipment to Chile. You can see one here being offloaded from the transport. And this is a photograph of one of the mirror cells that I mentioned earlier during the video. They were the red-shaped objects in the video. And this shows on the top surface of the cell are a series of basically shock mount springs. This is what the mirror rests on when it's not in operation on the telescope. And these also protect the mirror if there's a large earthquake to prevent the mirror from damage. Now, protruding up through the top plate of the cell are some of these hundreds of pneumatic actuators. They're arranged in a triple actuator arrangement so we can put forces, basically lateral and axial forces to support the mirror at whatever angle the mirror is at in the telescope. And we're building this as a test bed to verify that we can control the mirror to the precision that we need to control it with this arrangement of actuators. Once we're finished with the mirrors and we've shipped them to Chile, they will probably leave the port of Houston and travel through the Panama Canal to a port city in Chile, and then overland on the Pan American Highway, up the access road of the mountain to the summit of the observatory. And then we will lift the mirrors out of their transport containers and place them on the mirror cells. And the mirrors and the mirror cells then go into a very large coating chamber where we apply a reflective coating of aluminum to the front surface that's about 200 nanometers thick. We use about a half an ounce of aluminum per mirror, which forms the reflective surface. Then the mirrors are taken into the enclosure. They come up by crane, overhead crane, through a hatch in the observing floor, integrated onto the telescope structure. You can see them here again with the mirror covers protecting the reflective surface. Now, I've mentioned the importance of phasing the telescope and the fact that we have these large mirror segments with sizable gaps between them. We had to come up with a method for phasing these segments. So basically what we do is, using light from a guide star that's coming through the telescope, we take portions of light that are reflected off of adjacent edges of adjacent segments. These are 1.5 meter square areas. And this basically forms a series of two slit experiments, if you will, that form interference fringes. And we then disperse those fringes in wavelength, and we can tell the differential piston or the misalignment of the edges by the degree to which the interference fringes have rotated. So on the left, it shows you the interference pattern with 0 phase difference between adjacent mirror segments, and on the right with 10 microns of phase difference. So for our telescope, we're going to continually monitor the alignment of the segments and continually adjust them to keep them in phase. And we need to observe 3 guide stars for that purpose, and we do that measurement in the near infrared, where the atmospheric coherence length is long enough to assure a good measurement over the gaps between these segments. These dispersed fringe sensors that are used to phase the telescope are located in what we call our acquisition, guiding, and wavefront sensing system. There are 4 such units that are bolted to the top of the GIR, the 6 by 9 meter cylinder, and they look like this with a pick-off mirror that can be extended and rotated into the field of view, so it patrols around in the field of view to find guide stars. We've taken a prototype of this phasing system onto the Clay telescope at the Magellan Clay telescope at the Las Campanas Observatory, and we have a prototype of the dispersed fringe sensor prisms. This is what it would be like for the full giant Magellan telescope, and we have a smaller scale prototype in here where we synthesize a segmented mirror at the Clay telescope and see how well this approach works in the presence of various disturbances. Now I'm going to come back to this important topic of adaptive optics, or how we defeat the distortion in the Earth's atmosphere. This was first proposed by Horace Babcock, but in an era before there was the computer and sensor technology to make this work. And the basic idea is that as starlight is distorted through the Earth's atmosphere, if you can reflect that light off of a mirror that you can bend into a shape that will compensate for the distortion of the atmosphere by means of actuators that you can control, then the reflected light will be restored. You'll have the wavelength flattened back out. And this system was developed by the military. It was classified for a long period of time, but then it was declassified and is now commonplace in astronomical observatories. The challenge, of course, is that you need a deformable mirror, and you need to update the shape about 1,000 times a second because the atmosphere is turbulent and the distortion is ever changing. So we accomplished that on the Giant Magellan Telescope up at our segmented secondary mirror. This is a close-up of what that assembly looks like. And each of these secondary mirrors is an adaptive secondary mirror. It's actually going to be a 4th generation adaptive secondary mirror from the company Ad Optica in Italy. And each of these mirrors will contain 672 actuators, or nearly 5,000 actuators across all 7 mirrors. We're going to operate them at a 2 kilohertz bandwidth to do the adaptive optics for GMT. And locating them up at the secondary mirror gives us the ability to do correction of the ground layer disturbance, which is where most, or a good fraction, perhaps not most, but a good fraction of the distortion occurs in the atmosphere. And that ground layer correction allows us to correct over a wide field of view, so we can improve the imaging even for wide field observations. For areas of the sky where we do not have a sufficient number of natural guide stars, a technology has been developed called laser guide stars, where you fire lasers up through the telescope, and the lasers, if they're of the right wavelength, can excite the sodium atoms that are left behind, the trace amount of sodium in the very upper atmosphere by the burning up of meteorites as they come through the atmosphere. And you can excite emission, stimulate emission from those atoms and form synthetic guide stars, which you can then use for the adaptive optics function. Turning now to scientific instruments, I'm going to pick the pace up a bit. Our instruments are located again in the Gregorian instrument rotator. We have various instrument stations. So we can locate and move from one instrument to another during the night if necessary. This is the first generation of instruments. It's basically 4 very capable spectrographs. We have 2 spectrographs in the optical and 2 in the near infrared, out to 5 microns. And 2 of them are very high resolution and 2 of them are intended to be very high sensitivity and multi-object. The first light instrument, the first instrument on the sky will be this instrument we call G-clef. And this is an Echelle spectrograph, very high spectral resolution. This will be important for exploring the atmospheres of exoplanets to try to look for signs of life on those planets, and for having a very high precision radial velocity capability of 10 centimeters per second to look for the existence of exoplanets orbiting stars by measuring the reflex motion of the star due to the mutual tug of gravity. This is a plot that shows different stellar types. As stars become more massive, they become hotter and more luminous versus the orbital period of a planet. And on this plot, you can define the habitable zone, which is the distance from the star where a planet would be at a temperature where you could have liquid water, which we think is necessary for any form of life that we would recognize. And these different contours are different radial velocity precisions that you need to detect planets. Currently, radial velocity precision is basically this contour and to the lower left. The G-clef precision will be up here. So it'll be in the vicinity of being able to detect Earth-sized planets or nearly Earth-sized planets orbiting around sun-like stars. And all of this region will be accessible to the G-clef instrument. Another planet plotted here, these are all of the rocky planets around the habitable zone that are known, or at least were known in 2017. Proxima Centauri b is a known rocky planet orbiting a star in the southern hemisphere, and we expect to be able to image that planet, separate the light from the star, and characterize its atmosphere. 2 of our spectrographs can be fiber coupled over a wide field of view. This is being prototyped in Australia with fibers that are self-mobile with piezoelectric devices. They can move around on a glass corrector plate, change position. And I now want to talk briefly about some of the engineering challenges with the environment that we have to deal with in Chile. And one of them is the seismic hazard. Chile is a very seismically active area. The largest earthquake actually ever recorded occurred just off the coast of Chile. That was the 1960 magnitude 9.5. Our site in Chile, located on the map here with the star, experiences about 6 earthquakes a month. And in the last 5 years, this is the spectrum of earthquake magnitude that we've experienced. So earthquakes are a challenging environment for a telescope this size. So we've determined we need to do something to mitigate the hazard from earthquakes. And so we're borrowing something from the civil engineering realm. This is a cross-section showing our telescope, and it's supported typically, telescopes are supported on a very thick concrete pier, which is in contact with bedrock. The stiffer and firmer the interface, the better. We're going to split that ring wall of the concrete pier and place 24 friction pendulums around the wall so that when the ground moves laterally above a certain threshold, that it will allow the ground to slide around under the telescope and not transmit that accelerating force. So these are commonly used to protect things like the space shuttle in the California Science Center. You can see these friction pendulums if you visit there. And underneath the Pasadena City Hall, it was built in the early part of the 20th century. The entire complex is supported on 240 of these friction pendulums. So this is a novel application, and we've had to pay close attention to how to make this work without compromising the performance of the telescope. Another challenge we have is that we have to build the enclosure in such a way that the airflow over the enclosure does not add additional atmospheric distortion. So we did quite a campaign of computational fluid dynamics analysis to look at different configurations for the enclosure, and we still are using this to understand what kind of wind disturbances occur, how much they affect the image quality, and that's guiding our design of the enclosure and the telescope. This is a look at what the enclosure configuration looks like in closed up and closed to weather. During a typical night observing run where it's open and shutter doors are open to allow air to flow smoothly through. And we have the ability to block the wind if the wind is so strong it's causing excessive vibration or wind shake on the telescope. Currently, the enclosure has completed its preliminary design and is now in final design. And this is what the observatory site looks like today. We leveled the mountain to have enough room to place two 30-meter class telescopes. So we're building right now on this side of the mesa, and you can see the hard rock excavations for the enclosure foundations. Here's one for the telescope concrete ring wall for the pier, a trench for utilities. This is where all the rotating machinery will be located. And then we have enough room on the other side of the mesa to put a second such telescope in the future, or an even larger telescope if necessary. Now I'm going to say something briefly about the science. We have a beautiful science book which you can get from our website, www.gmto.org/resources. It was written in 2018, and it's written basically for so someone at any level of knowledge about astronomy can access this document and extract useful and meaningful information. So if you're a professional card-carrying astronomer, if you're just a novice, you can find this a good read. And these are the various chapters ranging from exoplanets and star formation through the life cycle of stars, the building of galaxies, the evolution of galaxies, cosmology in the dark universe, referring to dark matter and dark energy, and the very early period after the Big Bang. And some of the interesting science objectives for the observatory will involve exoplanets. We intend to locate and study planet formation, search for extrasolar life in the atmosphere of some of these planets. We are trying to understand better the supermassive black holes and how they evolved over time. They seem to have formed early on in the universe. We're also interested in looking for intermediate mass black holes. We know about smaller black holes when stars supernova and collapse, or you have an in-spiral of stars that form a black hole. And we know about supermassive black holes at the center of many galaxies, but we don't know about intermediate mass black holes, whether they exist. And so we want to study the motion of stars and galaxy or star clusters and look for evidence of intermediate black holes. Galaxy evolution, as I showed you in the earlier graphic, we're trying to understand how galaxies put themselves together, how star formation occurred over the life of the universe. And then cosmology and fundamental physics, trying to understand more about what this mysterious dark matter might be, dark energy, the tension that exists now in the Hubble constant, which may be an indicator that there's new physics to be discovered. And then, of course, the most exciting area are the discoveries that will be made by the Giant Magellan Telescope that we can't anticipate today. every time we put a new telescope, open a new window on the universe, we discover things we didn't even know how to ask questions of. And so I'm sure that some of those are in store with these extremely large telescopes. So with that, I think I'll end my talk and turn it back over to Larry. Let me unshare my screen.
Well, thank you very much, Jim, for a fascinating glimpse at all of the ingenuity and engineering that's gone into creating this telescope. And we're looking forward to, in the years coming, hearing about the results of observations made with the telescope. We have time for a Q&A session. Zoom participants can raise their Zoom hand or type their question in the Zoom Q&A panel. I will call on Zoom participants in turn to unmute their mic and ask their question. Zoom participants who don't want to ask their question aloud, please write that in the text and I'll read the question. YouTube viewers can text questions in the YouTube chat box and those will be relayed to me. All text questions will be read aloud for everyone to hear. Well, let's start with PSW member James Van Artstelem. He has 2 questions. Jim, if you could unmute your mic and ask your questions.
Yes, hi. I was wondering if you could talk about the mathematical modeling that was involved to calculate the proper curvature of the mirrors and to guide their polishing.
So that's a good question. So the polishing of these mirrors is a very sophisticated process. First of all, the optical design of the telescope follows a particular formula, so we know what shape we want the optical surfaces to be. These glass mirrors, although they're very stiff at the dimensions of the wavelength of light, they are still flexible. So the mirror is first supported on a polishing cell where the forces at each of the attach points are very precisely controlled. So that gives a known boundary condition to the glass. And then there are 4 different methods that we use to determine what the shape of the mirror is. The shape is so irregular to begin with that you cannot form an interference pattern by reflecting light off the surface. And so there are different methods. One method is to, in a very controlled way, raster scan like a hockey puck on an air, like an air hockey board. It floats on a thin layer of air, and you can measure the contour of the mirror, and that's used in the early stages. Then there's another method that uses light to reflect off the surface and model the contour. And then finally, when you get close enough to the correct shape, you can form an interference pattern and use that to guide the final polishing. So the polishing takes many months. It's an extractive process, not an additive process. You need to be careful not to remove too much material. So you converge on the proper shape very gradually and carefully.
We have a question from Wendy Friedman. Wendy?
Hi, Jim. Really enjoyed your talk. I just wanted to ask you, a lot of the risks, initial risks of the technology for the GMT have now been retired, as you have so eloquently described. And I wondered from your perspective, what you see as the remaining technical challenges to the GMT, the most significant challenges that remain.
Some of the most, hi Wendy, it's nice to hear from you. Some of the most significant challenges remaining are the construction of off-axis adaptive secondary mirrors. We're in the early stages of manufacturing the first of those assemblies. I should say that the National Science Foundation was generous enough to provide us with about $17 million for technology work on adaptive optics and phasing of the telescope. And some of that is going towards manufacturing the first off-axis adaptive secondary mirror. Those flexible mirrors are 1 meter in diameter, but they're only 2 millimeters thick, so they're extremely thin and fragile. And this is what allows us to bend them in the complex shapes to do the adaptive optics correction without risk of fatiguing or damaging them. But no one's ever built one of these things with an off-axis shape, so that's a technical challenge. And then the area of phasing the telescope and verifying that we actually can achieve this in the face of realistic atmospheric disturbances and other effects has caused us to build 2 additional test beds. These are also funded with funding from the National Science Foundation. So we're building those test beds, and that will give us risk reduction at a higher level of assembly of putting the various components and control systems together to verify that, in fact, we can achieve the phasing. So those are two of the major challenges. We also have under contract the development and fabrication of the telescope structure. It's a very large structure, and it has to track very smoothly and provide the kind of stiffness that we need to position and support the optical elements. There's not so much technology associated with it, but it is a very large assembly. So we're eager to get on and retire that risk as well.
We have a question from Bob Terry. Bob, PSW member.
Okay, you hear me?
Yes, we can hear you.
Yes.
Oh, good, good. I was curious, the structure appears to be somewhat open and you have windscreens, and how do you mitigate the problem of dust and grit blowing through the housing and getting on surfaces? How do you protect that very valuable optic?
Well, that's a good question. How do we keep dust out of the enclosure because it's open and the winds can be pretty fierce? Well, the first thing we'll do is we'll put a particular kind of gravel on the ground to try to prevent fine particles from being blown up right next to the observatory. But some amount of dust and grit will get into the telescope, and in particular on the surface of the optics. And we want to keep the surface of the optics as dust-free as possible. So probably on a daily basis during the day shift, since we only do observing at night, we will go through a cleaning process. It's customary to use what's called CO2 snow, which you can blow on the optic and dislodge dust. And we also have a plan to do wet washing of the mirrors to keep them as clean as possible and for the reflective coating to be as durable as possible. So we will take some cleanliness measures on the telescope. The hydrostatic bearing film that the azimuth and elevation bearings run on are protected by labyrinth seals and other means to try to keep dust, and the oil is recirculated and filtered to keep it out of the bearing surface. So there are some things that we can do.
But not a trivial matter at all.
Not a trivial matter, but one advantage of a telescope this large is that the telescope is fairly high off the ground compared to a smaller telescope. And so we have some experience with this.
Thank you.
Let's just take a second to say hello to some of our viewers from afar. We have hello to you on the west coast of Sweden, and hello to you in Medellin, Colombia, and in Montreal, Quebec, and in Australia. I'm glad that you're joining us. I hope you're finding this as interesting as I am. I have a question from Carl Merrill, a molecular biologist. Carl?
Thank you. You mentioned using the telescope to look at black holes. And recently we've had an image of a black hole by a collection of telescopes that were all matched with precision timing. And then they analyzed all the data at a central location. So the question is, how will this telescope, what information will this be able to give us that you can't do that way? or how will they work together, or what's your vision for that?
So the Event Horizon telescope image, a stunning achievement with radio telescopes across the globe. So those images were constructed from radio wavelengths, and in the radio part of the spectrum, you have the ability to demodulate the signal and record it with precise timing data that you can then use to synthesize essentially composite images. We do not have the ability to do that in the optical part of the spectrum. So our approach to exploring black holes will be more conventional. We will be observing with the maximum resolution of the telescope the environment around black holes and studying the emission of material that is in the accretion disk or is in falling across the event horizon, and understand better the physics of those very high gravity environments.
Thank you. So basically, you're saying you could not combine a set of telescopes, even if they were close by, and using optics for that.
So if the telescopes are in physical proximity, then you can combine the light into an optical interferometer. That was done at the Keck Observatory. So the two 10-meter telescopes were linked together optically to form a 100-meter baseline interferometer. And that gives you the ability to image using the diffraction limit of a telescope whose aperture is equal to the separation between the telescopes. But there's a limit to the distance over which you can do that. So there are no telescopes in close enough proximity to the giant Magellan telescopes where we could do that. Now, in principle, if we built a second giant telescope on the other side of the mesa, we could link the two together as an optical interferometer and do what you're describing.
Thank you.
Okay, we have a question from a YouTube viewer. Forgive me if I get this wrong. Brian Camelli, he says, very exciting, very large project. Doesn't it require a large maintenance? And what is the life expectancy of the GMT?
All very good questions. Let me answer them in reverse order. So the lifetime we've defined for the observatory is 50 years. And so we're doing the seismic design, for example, so that there's a very low likelihood of catastrophic damage, even in the face of a survival level earthquake that might occur near our site. So 50 years is the operational lifetime, but of course, there's nothing to prevent the telescope in principle from having a much longer life. There is quite a bit of engineering and maintenance that's required on something this large and complex. So there will be a sizable engineering team that during the day shift will perform various maintenance functions. The interval for maintenance will vary depending on what the subsystem or component may be. But yes, it's the telescope is so large that you can be on part of the telescope and not be able to see somebody on another part of the telescope. So just coordinating between people working on the telescope will probably require some kind of a radio communication system. And of course, the safety aspects of working on something like this are also a bit more challenging. There are confined spaces, there are fall hazards, there are many hazards that we have to engineer for.
We have a question from Brett Magaram, who's PSW treasurer. He's a structural engineer, and he asks, if you're constantly deforming the mirrors many times per second, does fatigue become an issue with the mirrors or the aluminum coating? What is the expected lifespan of the mirrors and their coating?
Another excellent question. So you're referring to the adaptive secondary mirrors, these mirrors that we deform at 2 kilohertz bandwidth. So as I mentioned, these mirrors are very thin. They're 2 millimeters thin. So they're actually very thin face sheets of glass or zero-dur material. And the amount that we are deforming them is very slight. Again, we're deforming them on the scale of the wavelength of light. So while we're moving them very rapidly and high cycle exposure, the amount of stress that's developed is quite limited. It's quite low. As for the reflective coating is probably going to be about 1,000 times thinner than the diameter of a human hair. And so again, it's not going to develop very much stress.
We have a question from PSW member Connor Nixon. He's a member of the General Committee. He's a space scientist at NASA Goddard. And Connor?
Oh yeah, well, first of all, I want to congratulate James on the technological achievement and really fantastic talk. And I wish the GMT project the best of luck. My question is, what is the long wavelength cutoff of the telescope? I work a lot with the NASA IRTF, so I was interested about what are the longest wavelengths you eventually envisage being able to reach with instrumentation? And is it more limited by the atmosphere or by the telescope itself?
Well, our current generation of instruments will operate out to about 5 microns. I think the long wavelength limit is really going to come about from the fact that there will be thermal emission. The telescope is at ambient temperature. So at some point, when you're approaching 10 microns or beyond, you're going to be better off going to space to do the measurements or to have a cool telescope in some manner. So in principle, the telescope will support longer wavelengths, and indeed we may field instruments at longer wavelengths. But it's the thermal IR that will set the background limit.
Thank you.
There's still reasons to go to space.
We have another question from a YouTube viewer. Again, apologies if I pronounce your name wrong. It's Yang Chu. He asks, what fraction of light, energy, or information is lost after each reflection?
That's a good question. So when surfaces are coated and the coating is clean and fresh, the loss is a function of wavelength, and that's partly what you take into consideration when you choose a coating. But I would say a good coating will lose less than 1% typically in most wavelengths, up to a couple 3%. The challenge is that if you have many reflections, they're multiplicative. So you lose 1%, and then you lose another % on top of it, and it's not additive; it's multiplicative. And so you want to keep the number of reflections to a minimum.
Okay, we have a question from Noah Block. Hi, Noah. You can ask your question.
Hello, can you hear me?
Yes.
Yes.
I was just like to ask, who's going to be analyzing all the data that's generated by the telescope? Will anyone be able to log on and just get the data, analyze it themselves, or does it go to a few specific institutions?
So that's a very interesting question. So what I find interesting is that the history of the world's largest telescopes is really a history of telescopes being in the hands of private institutions or individuals. It has not traditionally been the role of government, at least not in the United States, to be involved in developing the world's largest telescopes. And for that reason, the institutions that have paid for the telescopes and operate them have more or less exclusive access to the data. And this is what it allows institutions to attract the best and brightest minds to their faculty, is to give the faculty access to uniquely powerful instrumentation. Now, the data for the private consortium would be made available to the consortium. But I have to mention that we are in dialogue with the National Science Foundation about the US government becoming a participant with the Giant Magellan Telescope. They would become a partner, and their interest would be in getting a portion of the observing time of the telescope, possibly a sizable portion of the observing time, and making that available to the entire US astronomy community. So in some sense, a fraction of the telescope time would be a national asset. And then anyone could apply for time and go through the time allocation committee process and make use of the telescope and have access to the data. So the NSF has not made a decision whether it wants to proceed down that path. There's an important decadal survey that the US government is undertaking at the moment. The National Academies of Science and Engineering undertake decadal surveys every 10 years in various parts of the scientific domain and determine what the nation's priorities should be in science for the next decade. And NASA, the National Science Foundation, Department of Energy, these agencies that do science pay attention to those reports and those priorities when they set their programs and their funding and their budgets. So the decadal survey is expected to be released for ground-based, or for astronomy, I should say, and space science is expected to be released sometime between the 1st of April and the end of June. And so we briefed the decadal survey on a concept called the US Extremely Large Telescope, where both the Giant Magellan Telescope and the 30-meter telescope, which is planned to be built in the Northern Hemisphere, would join forces, if you will, with the National Science Foundation to give the US community access to both of those telescopes in both hemispheres for general research purposes.
Thank you very much.
Isn't it the case, though, that even if it remains in private hands, after a certain period of time, the data will be available for more general use in the community?
I think the trend is to make data available after a period of time in the community. The data handling arrangements or the data sharing arrangements are still being negotiated within the consortium. And so I can't give you a definitive answer on how or when the private consortium's data would be made available more broadly. Perhaps Wendy, actually, who used to chair the board of the Giant Magellan Telescope, would have a comment on that.
Unmuting here. So a comment on whether the community would have access. Sorry, I just temporarily got interrupted.
Would the broad community get access to the private consortium's data from the GMT?
Yeah, ultimately the goal is to make all of the data accessible within likely a 12-month period. So that is what facilities in space now do. So for example, Hubble Space Telescope, as a principal investigator, you would apply for time and you would have access to those data for some proprietary period. And the idea with the GMT also is to have proprietary time for the initial investigator to do the science that they propose to do, but then make it accessible to the general community through an archive. So that has been the idea of the GMT since its inception, yes. And the experience with the Hubble Space Telescope has been that about 50% of the science now, the papers that are being published, are coming through data in the archive. And making the data more generally accessible has clearly been better for the scientific community. people come up with novel ideas in the future, and science is better overall if you make it generally accessible.
Yep, that is definitely the trend, and I see that continuing.
Yeah, from what little I know, there seems to be a pretty strong consensus that that's the way we should go. Not we, but that's the way it should be done. Said it did sort of related question as to what extent and is artificial intelligence and those kinds of programs going to be a very important factor in how the data from these GMT and the other very large telescopes is analyzed, interpreted, and the results are produced.
So I'm not an expert in this area, but my instinct is that artificial intelligence will become increasingly important to the kind of big data analysis that Wendy was describing before. There are increasingly massive archives of data of different wavelengths from different instruments. And if you want to get an understanding of how the physics of the universe works, you need to be looking across the spectrum in various kinds of ways and aspects of the data. And I can imagine that artificial intelligence will be adapted to finding patterns and finding correlations and other relationships in the data. And so I would imagine that will play an increasing role.
I have a question from YouTube again, from PSW member Will Angel. I don't think he's related to the telescope maker, but maybe. Will, I'm sorry, Will, go ahead. Oh, I'm sorry, I have to read this. I'm a little confused. Will future telescopes continue becoming large individual telescopes, or will telescope arrays and interferometry play a larger role in breakthrough telescopes in the future?
Well, that's an interesting question. I would say that I would have expected interferometry to play a larger role than it has in recent years. It's difficult to build large monolithic telescopes. There are various ideas out there for sparse aperture telescopes where you would space the mirrors out maybe on a common mount. There's something similar to this right now today in the large binocular telescope that was built by the University of Arizona, but you can imagine, for example, a ring of these 8.4 meter mirrors on a large diameter, which you could synthesize as a sparse aperture array or an interferometer. So I think you're likely to see growth in both directions, larger monolithic telescopes as well as more innovative and creative designs. But time will tell.
I have a related question. So all of these monolithic mirrors being made at Arizona are 8.4 meters. Is there something magical about 8.4 meters, or that was just the practical limit at the time?
Well, you probably could make a larger mirror, but you'd need to get a different facility. And you have to think about how you're going to move the mirror from the mirror lab to your observatory location. And these are already so large when they're in their transport containers. They're about 10 meters across. It gets difficult even to go down a freeway with something that's much larger than that. So I think there just becomes a practical limit of moving the hardware around. But I think 8.4 meters is a comfortable size from the point of view of the process is pretty well established by now. They have a very high success rate. My fingers are crossed that our mirror number 6 will come out successfully when it's cast tomorrow. But I suppose someone could build a mirror factory on their observatory site and not worry about having to move it down the freeway.
Practical considerations, not having to do actually with the technology for casting the mirror.
I think it's just practical considerations.
We have a question from relatively new PSW member, Firas Assam. Again, apologies if I have not pronounced your name properly. Firas, you have to unmute your mic. Well, technical issue, I can read the question. He wants to know how much it costs and when it will be ready.
Two very practical questions. So the Giant Magellan Telescope total project cost is estimated to be about $2 billion. We expect to have first light of the telescope by the end of this decade. That first light will probably occur when we have 4 of the 7 segments on the telescope. We are going to be commissioning the telescope as we add optics mirror segments to it. We probably won't build out the full observatory until the early part of the next decade.
We have a question from a YouTube viewer, a friend of ours down in Colombia, South America, and he has a very timely question. He wants to know in essence, he wants to know whether or not this telescope's ability to observe will be affected by the large constellations of satellites that are being put up by SpaceX and others. And if so, what's the plan to deal with that?
Yes, that is a timely question. Yes, so there are plans to put many thousands of satellites into Earth orbit. This is probably a bigger issue for telescopes that are designed to do surveying of the sky, where they have a very large field of view and they are covering the sky rapidly in a synoptic sense. So the Vera Rubin telescope, for example, does exactly that, and they will not be able to avoid satellite trails coming through their imaging. And so they are developing data analysis techniques to identify where the satellite trails have affected the data and ways to remove those signatures from the data. For telescopes like the Giant Magellan Telescope, where we have a smaller field of view than a survey machine, we will probably have the ability to schedule our observations, knowing the trajectories of the ephemerides of the satellite orbits. We will probably be able to avoid them to some extent. And because we are observing over a small field of view, we'll be less susceptible to contamination. I know that the American Astronomical Society and the International Astronomical Union have committees that are studying this issue. SpaceX has been very receptive to the issue. They have, they're very supportive of astronomy and science. They don't want to negatively impact the field. And so they're actively working to design the satellites to be minimally reflective and to minimize their signature on the sky. Possibly more threatened are the radio telescope observatories on the ground, because the emissions from the radio emissions from the satellites will possibly become an issue for them. So this is something that we're trying to better understand and develop methodologies to work around it. And the satellite manufacturers are on their end trying to find ways to minimize the impact the satellites will have. But it is an issue.
I have a question from Glenda Turner. I think Glenda can ask this question directly. Oh, Glenda.
Yes, thank you. Excellent presentation. I was wondering if you could speak a little bit to how the science operations would be managed and located. Like, do you have operations centers? How many different locations does your total project encompass?
So that's a good question, and a question that has not finally been resolved. There is likely to be an operations facility, probably in La Serena, which is relatively accessible to the observatory. There is likely to be a set of remote observing facilities that you could go to operate the telescope. We envision a mixture of what's called classical observing, where people travel to the telescope to make their observations, and remote observing. Part of the observing strategy is to what's called queue schedule the observations to match the observations against the exact observing conditions that you have. Some observations can be made only when the weather is pristine. Other observations can be made when the moon is out, for example, which is a bright straight light source. So the operations plan is still in development and is something that will be documented, and we'll have discussions with the National Science Foundation as well. We are working with the NSF's NOIR lab, their optical and IR research laboratory in Tucson, Arizona. They have a lot of experience operating observatories for the National Science Foundation and doing queue scheduling. And so we're working with them on the various roles that they would have in the data analysis, and possibly also tools that we could make use of for scheduling real-time operations of the telescope.
Thank you.
I have a bit of a follow-up question to that. So a lot of these instruments are, there's no need for an astronomer to be looking through an eyepiece to observe anything. And setting up the instruments is a sort of a technical exercise in a way. And the data gathering, is all digital, and it gets pumped down to, to a screen, to a computational resource, be stored. What's the need for, somebody who's doing the astronomy to be on site as opposed to down at the ocean in, a more comfortable environment?
Right. So you're quite right that with all of the automation and technology, you can do observing remotely. In fact, there are telescopes that operate where there's no one at the telescope. They're completely robotic. You can get on your laptop from your sailboat and do observing remotely. What other observatories have found, the Gemini Observatory, for example, is that when your user community never visits the observatory, they lose a contact, almost a social contact with the observatory. And so the sense of ownership, connection, understanding of how the observatory operates are enhanced by having a fraction of the observing done in this classical mode. So I think the bulk of observing will be exactly as you described. It'll be remote. And there'll be an engineering team that services the telescope during the day, and people to assist the observing at the telescope at night. But the bulk of the observers will probably not be traveling. But I think it's important to keep that human contact with the observatory, at least at some level.
Thanks. There are two last questions. We'll end with Bob Abramson's question, but before that, a question. Is this scalable? Could you add another ring of 8.4 meter mirrors in a subsequent design? And would it be worthwhile to do that?
Yeah, so I think absolutely it is scalable. In fact, I think I've seen a drawing of the telescope as another ring of these 8.4 meter mirrors. The tendency is once you've mastered a particular approach to scale it. So for example, the 30 meter telescope is scaling up the approach that was taken for the Keck 10 meter with hexagonal segments. Keck has 36 segments. The 30 meter telescope has 492 segments. And the Europeans are taking a similar approach, and they have, I don't know, a semi-infinite number of segments. So what they've done is they took a system that worked with Keck and they've scaled it. And I think the same thing is likely to occur with the giant Magellan telescope.
Thanks. Last question from Bob Abramson. Bob?
Yes. When we begin to make new discoveries with the James Webb Space Telescope in coming years, can you maybe identify a couple of examples where those discoveries will pave the way for certain investigations that the GMT will be well suited to pick up on and leverage and or synergize with?
Yeah, a very good question. There has been and will continue to be a synergy
Bob,
between.
can you mute your mic, Bob?
Sorry, there has been and will continue to be a synergy between ground-based astronomy and space-based. There are strengths in both types of telescope. For example, James Webb is going to operate out at longer wavelengths and will have the advantage of the kind of stability that you get being in space. So it will no doubt be able to make observations that we cannot make, at wavelengths we cannot reach from the ground. And I think that there will be objects of interest that will be discovered by James Webb where, we want to get a spectrum that requires more light, and we can bring a ground-based telescope to bear. There was a tremendous amount of synergy between the Kepler mission, which was doing the exoplanet search, and ground-based telescopes. Ground-based machines were key to the follow-up from Kepler to determine whether the Kepler detections were real planets or whether they were false alarms. So there will be a synergy not just with James Webb, but with the all of the space assets. Again, there's a complementarity of strengths and capabilities. So I think we're stronger because of that synergy between the two.
Well, I wish we could go on, but thank you so much for giving this informative lecture. We really appreciate the time that you spent both in giving the lecture, answering the questions, and the time that we spent together beforehand. So thank you very much. As you know, you have a rain check on the reception and dinner, social hour, and after party that we can't really have because we're not permitted to meet in person. But when you're in DC and the stars align, so to speak, you are welcome. And we hope you will join us for a different PSW event.
Thank you. I look forward to that when we can travel once again. I can meet you in person and meet some of your members. I very much appreciate the invitation. I've enjoyed the conversation.
Terrific lecture. Thanks so much. And thank everyone for joining us. The recording of tonight's lecture will be available to everyone on the PSW Science YouTube channel and in due course on Vimeo and via the PSW Science website. Please share the links with your friends and subscribe to the channels for notifications on new postings. And do not hesitate to join. It's easy to apply for membership using the join button on the PSW Science website. And before you go, a few important closing announcements. The next lecture, I should say before I get to the next lecture, I want to note once again that PSW will mark the 150th anniversary of its founding on March 13th of this year, 1 week and a day from today. We will not, unfortunately, be able to celebrate the occasion in person on that date, but we will be doing so when it is again safe and permitted for us to get together. PSW's sesquicentennial will not go uncelebrated, and indeed, we will be commemorating the Society's first 150 years and looking forward to its next 150 years throughout the year. Watch for special announcements. The next lecture will be in 2 weeks, on March 19th, 2021. The speaker will be Kate Kraft of Johns Hopkins Applied Physics Lab. She will be speaking on the Europa Clipper mission. This will be our second lecture on missions to Europa, the first being Christopher Waldman's talk on the German Triple project. That video is available on the PSW Science YouTube channel, Vimeo channel, and via the PSW website. The 2438th meeting will be on April 9th. The speaker will be Hod Lipson of Columbia University. He will be speaking on the 5 ways of AI, past, present, future. This is the first of what we hope will be a series of lectures exploring how advances in AI will affect and perhaps fundamentally change science. The 2439th meeting will be on April 23rd. The speakers will be Simon Bennett and Dan Irwin of the London Crossrail Project. They will be speaking on the construction of the new Elizabeth Line subway, cutting underneath London, sometimes within an arm's length of its loftiest skyscrapers, successfully completed with the use of a digital representation of London underground and above ground. The 2441st meeting will be on May 21st, and the speaker will be Bill Powell of the State University of New York College of Environmental Sciences and Forestry. And he'll be speaking about the chestnut blight and about genetic and molecular biological approaches to creating a blight-resistant American chestnut tree. Additional lectures of the spring lecture series will be posted to the PSW website. Please check there often for updates. And before we go, let's not forget to thank the crew, James, Cameo, and Robin, for producing tonight's event. Thank you. And I will now adjourn the 2436th meeting of the Society. I wish everybody a wonderful evening or rest of the day, wherever you happen to be. The meeting is adjourned.